There we go. All right, so this time is going to be between Zoom and YouTube. So if you can hear me, then we can go ahead and get started. Are we good?
Yep.
Okay, excellent. All right. So what we'll do today, the first part is to work on um, the lab from Tuesday. So that's what we'll do first, is to work on the lab from Tuesday. And I will go ahead and explain things along the way if people have any questions. Sorry?
Oh, sorry, wrong. Oh,
All right. All right, so we're going to get started here. So the first thing is, I want to emphasize that labs are they're kind of cumulative in a way, in a strange way, in the sense that the earlier labs will give you the tools to do the later labs. So that's why, in the 3x3 Part 1 lab, which is the one that you did on Tuesday, there are certain elements in that lab that relies on something that you have learned already, such as the use of splitters, multi-bit pins, multi-bit gates, and so on. So that's the first thing that you probably need to be aware of. So I'm opening the lab so that I can go through exactly the same instructions. And then on the side, let me go start up my Logisim. So I'm just looking for a command line prompt, and that was hidden. So let me go start with a new terminal first. Okay. All right. So there we go. We got Logisim, and I'm gonna move it into the part that you can see in OBS. My camera is off, because it picked up the wrong window, so you're not gonna see my face for the time being. I guess I can turn that on in Zoom, but I'm not going to do that. All right, so we'll first follow the instructions of the lab and create these elements in Logisim. So we'll pick up the pins. So first of all, it's good to pick up the pins from the toolbar because they already have the right settings in it. So it's good to pick up the input pins. We need 3 input pins. All right.
Yes, sir. Are you able to please mute yourself?
Hmm? Say it again.
Are you able to mute everybody?
Um, Let me see. You mean on Zoom?
Yes, please.
I probably can. Let me get through the control stuff first. Yeah, we got 53 people on Zoom right now. And okay, so we got some chats going on, but I will not read the chats from Zoom. And I'm not sure how to do that because I don't use it very often. I can see the people here. I can mute all. I think that might work, right? Let me try it. There we go. So is that working?
Looks to be good.
Okay, because you can still participate, using the voice channel in Discord. So I'm just muting everybody from Zoom. But on the other side, on Discord's side, everything should still be working. Yeah, my camera is showing a Google tab. I can turn that off if it is distracting. So we'll turn that off. There we go. Nope, it's not even turned off. Nope, that's not it. There we go. Okay. All right. So getting back to Logisim, there are 2 3-bit pins. So X is a 3-bit pin, and Y is a 3-bit pin, and then K0 is a 1-bit pin. So we'll go ahead and set all of those up like so. All right, and then we have tunnels. Tunnels are also a part of wiring, so we go pick up some tunnels over here. And every time you pick up a new component or every time you start to use a new component, it is important to understand where the actual connection point is. The technical term of the connection point is quote unquote the port. So in the case of a tunnel, the connection point is only on the pointy side, the other side has nothing to connect to. So even if you have a wire that seems to be going to a tunnel, it's not really actually connecting if it is not connecting to the pointy side. So you have to kind of keep that in mind because a few people, ran into this problem on Tuesday because they were connecting to some place, okay, that seemed to be touching the tunnel, but since it's not connecting to the pointy side, it was not an actual physical connection. Okay, I'm reading the text in the text channel. Yes, you can still unmute yourselves, but by default, everybody is muted first. So I just muted everybody on the Zoom side. Um, oh, okay. All right, so I'm just gonna continue with the lecture at this point. All right, so the tunnels, just like in the pins, they also have a number of bits. So we need to make sure the number of bits are matching between the input pin as well as the tunnels. Now the tunnels also can be labeled. Now the label of a tunnel is significant because every single tunnel that has the same name are logically connected and they are case sensitive as well. So this is really, really important because if you don't label a tunnel, it is not connected to anything. So that's the first part. And let's see, I'm trying to switch to the background. Okay, I can just click it. So that's the first part. And then the second part is to draw this part also in the main circuit. There are a few ways to do this. This tunnel, by the way, should be named K0. All right. All right. So thank you for helping me, to let the people who come recently to know that we are not using Meet and instead we are using Zoom today because I did something and messed up my Meet settings, and I'm gonna have to fix it after today's lecture. So you can do a duplicate, and once you have a duplicate, on multiple items, you can change the facing of all the items at the same time. So this is kind of a really convenient feature because we don't have to do it, one by one. Now we go back to the notes. Go back to the question, and we got 3 gates here, and then we also have 3 tunnels over here. So at this point, the important part is to remember the definition of what is P, what is G, and what is Q from the lecture and also from the notes. This is also why it is important to read the notes before class, because people who have read the notes before class, they would know that these terms are defined. They may not know exactly why they are defined the way that they are, but they can find the definitions. They know that P is in section 6, defined in section 6. They know G is defined in section 6, and Q is defined, I'm guessing, in section 5.1. And that is why it's important to kind of read the notes ahead of time and also review the content of what we have talked about ahead of time. All right, so now we are moving into the gates. So we got an exclusive OR gate, okay, and everything needs to be kind of made smaller. And also we only need 2 input pins. Now it's important not to have input pins that are not connected, okay. I'm not going to take any points off, from before, but from now on, you guys have to make sure that all input pins are connected to from something. Don't leave them dangling. Nope, YouTube, the audio should be on. I'm streaming everything from OBS to YouTube, and I know the audio is up. Alright, so now we have the other two gates. Okay, one is an OR gate, and the last one is an AND gate. Okay, so there we go. And all of these would need to be changed, and I'm suspecting you can select both. Okay, so this is really cool. If you select both of them, you can change both from 5 input pins to 2 input pins, and then change both from medium size to the narrow size. So this is rather handy. Okay, it's not really a must-have feature, but it is really handy to have because if you need to do the same thing to multiple gates, even though they're different kinds of gates, it still works. All right. And then we go back and then we make more tunnels. Okay, so we go back to wiring, and then we pick up 3 more tunnels over here. So one is a 3-pin P. So when we have a 3-bit pin, oh, I take it back. When we have a 3-bit tunnel called P, that means inside we have P0, P1, and P2. And then likewise we have G is kind of configured the same way. So we have G here. It is also a 3-bit tunnel. And then the last one is P, G, and Q. So let me duplicate this one more time, and this time this one is Q. There we go. All right, so the first big challenge is to find out, how are we making these connections? And I obviously have all the ordering of the gates and the ordering of P, G, and Q. They are all kind of messed up intentionally because I want you guys to think about how to make those connections. Because when you think about, okay, how do I make those connections, you kind of have to think about what about the definitions, right? P is defined to be the disjunction between x and y, G is defined to be the conjunction between x and y, and then Q is defined to be the exclusive OR between the x and y. And I'm not gonna I'm not gonna repeat where you find all those definitions. They are all in the modules, okay? And we talked about it in the synchronous lecture as well. So it's important to take notes. If that helps. You can also pre-read before the class. So it's kind of you have to find out what works for you. Okay, that's kind of the bottom line is you have to find out what works for you. Because one approach that works for one person doesn't work for the next person. So I'm just going to shuffle around the tunnel a little bit so that they are finally aligned with the gate that basically would feed to them. So Q is coming from the exclusive OR, and P is coming from the OR, and then G is coming from the AND, and obviously I have to change the gate to be also 3-bit wide. So now that we know that really cool trick, select all of them at the same time, and then change all to 3-bit wide, and now we have all the problems solved at the same time. So now we just need to hook up X to all 3 of the gates, like so, and also do the same thing with Y. Okay. And K0 is not used in this case because none of these 3, okay, Q does not utilize K0, P does not utilize K0, and neither does G. So this is what we should have accomplished by the time we are done with, I believe, question number 2. So let me check. Nope, not that window. This one over here. So by the time we are done with question number 2, that should be all set up. And now we can move on to question number 3. Question number 3 wants you to set up the subcircuit called K1. Okay, and so K1 is not the really difficult one. Some of the other ones are a little bit more difficult. So let me see if I can quickly. I can do this. I can open a new tab. And then I move it close to the other one because this way it's easier for me to remember which tab is which tab. And then when we go back to the notes on Tuesday, which is binary addition, then we can find out, what the definition looks like. Now, I don't remember the definitions, and I do not need you to remember the definitions either, but you should probably know where to find it. Okay, so all of the definitions that we would use in this circuit, they're all in section 6 of this particular module. So we can see how K1 is G0 or P0 K0. So the important part is, it's not just G itself. It is not just P itself. It's not just K itself. We need just one of the bits of the G and the P's. Okay, so that means, when we create that subcircuit, okay, so we go to project and then we say add circuit, and we call this one K1 because it really is just used to compute bit 1 of the carry. So the first thing is, we create the input pins. So it's about the same exercise as we had before. One is P, and it is 3-bit wide. And then the next one is G. It is also 3-bit wide. And then the last one is K0, which is only 1-bit wide. So here's K0. There we go. All right, so now we have the output pin. So the output pin, I can draw it all the way out here, and the output pin is going to be labeled K1 because that's what we're trying to compute. And then I can go back to the notes and then find out that, okay, K1 is defined to be G0 plus or P0 and K0. So I need an AND gate first, and then we need an OR gate before we get the actual output. All right, so what we do now is to go to gates, okay, or go to here too. So you can pick up an AND gate from there, and then pick up an OR gate also from there as well. And we also know that both of these only have 2 inputs in this case. So we change the shape and make sure that they only have 2 inputs, like so. And then we have to figure out, how to wire the P, G, and K0 as input pins to the gates, and then from the gates to the output pin. So the first thing we need to do is to remember, okay, go back to the equation, and we know that we don't need the entire G because G has 3 bits in it. We just need bit 0 in this case. And same thing with P. K0 is a single bit already, so it's not an issue. So we'll work with P0 first. Okay, so we go back to Logisim. We look at this P, and then we just say that we need one of the 3 bits. So we go back to wiring, pick up a splitter, and the splitter is the top. There we go. And if you don't want to make it look nice, okay, the quickest way to do this is to basically say we need a 3-bit splitter that is split 3-way. Okay, so this is the kind of really quick and ugly way to do it because we get all 3 bits all at the same time. Even though we don't need all 3 bits, it's okay to leave some of these pins unconnected because they are coming from an input pin, and it's okay to leave input pins unconnected. That is not a problem. So we know that we need P0 and K0 to be ANDed together. So to make the design look just a little bit nicer, we hook it up like this, so everything seems to be aligned, and then K0 goes to here. So what this has accomplished is it has done this part here. P0 and K0 is now done. Now G0 doesn't need to be ANDed with anything, so G0 is just kind of by itself going into the OR gate. So now we have the output of the AND gate and also G0 by itself going to the OR gate. The ordering is not really important because OR is commutative, so that means it doesn't really matter which one goes to the top port and which one goes to the bottom port. And this is how we make K1 as a subcircuit. You can test it if you want to, but when you are testing this, you have to remember that this is P and this is G. They are not X and Y. Okay, so that's the important part when you want to test this particular subcircuit. So I'm going to go back to the appearance mode of this, because without any type of documentation, it's really kind of easy to lose track of which pin is which pin. So I would use the text tool and just at approximately the right place, type in, P, G, and K0. Okay, and you can always drag them, into the right place. If you cannot, put all of these labels at the right place, when you first use the text tool. So the space is really kind of cramped here because the design is really small, has a small outline. But it's okay. It's not really that big of a deal. And then I use K1 as the overall name of the subcircuit. And we also want to, yeah, that should be good. Alright, so I'm looking at the text channel. That would be wrong, yes, because if you look at the splitter, it is using bit 2 instead of bit 0. So it is incorrect. Alright. And then the next question is when you use K1 as a component, if you hover over the pins, it tells you the name of the pin label. Not sure when you are using it, but when you hover and point to it, it will show you in a picture-in-picture kind of format, that the pin that you are clicking on is corresponding to which pin in the actual design. Is that what you meant, Nathan? In the main circuit view. Oh, okay. Oh, it will give you the name of the pin. Oh, okay, I see. Okay, I see what you mean. Okay, now I see. So we'll go back to main, and we'll pick out K1 as. So what you see over here, as the components, these are kind of like classes. In other words, until you put one of these components into the main design, it doesn't actually exist as an object. Okay, so these are classes, but when you click on one and then you put it into an actual circuit, then it becomes quote unquote an object. So I think what Nathan means is, if I hover over this, then it would tell me what the name of the pin is. Let's see. Nope, that doesn't work. Try the unlabeled one. Unlabeled. I think my mouse cursor is blocking it. No, I don't think so. I did not label the pins. I did label the pins inside the K1 circuit. So if I go to the K1 circuit, these pins are labeled. Somehow that did not happen with me. It did not, when I hovered in the main circuit, it did not show anything. Okay, well, it's okay with me because I explicitly labeled all of these pins, so it's not that big of a concern. Under my cursor on hover, did it show? I don't think so. I don't think I see anything. I don't see a box. Oh, okay, I see. Okay, because my mouse pointer is covering it. That's why. Okay, because I got a big pointer. I got a big, mouse cursor, and if I had chosen a smaller one, I would see it. You guys can probably see it too. You can see the very faint blue outline. That's at the lower side of the mouse cursor. Okay, there we go. Cool. I never realized that part because I have always used such a big mouse pointer, so has always covered that box from before. All right. Cool. Okay, now we can move on to, go back to the notes and go back to the questions, right? Over here. And we are now in question number 2. We are now in question number 3, actually. And then let's see. So this one is only concerned about K1. And then question number four is to construct K2 and K3. So we'll go ahead and do that too. All right, so between K2 and K3, it's going to be a little bit more complicated. So one thing we can do, if you're lazy like I am, you can go ahead and create the subcircuits first. So we can create a K2 and then we create a K3. There we go. And we go back to K1. And what I'm doing here is I am going to select this entire thing, copy it, and then go to K2 and paste it. So yes, I know some of these components cannot be reused. Okay, so we get rid of the things that I cannot reuse, but I still end up with a template that I can actually reuse. The splitter I can reuse, the input pin, output pins I can reuse. So I still get a good chunk of stuff that I can reuse, and then I have another copy and paste from here to K3 like that. So now K2 and K3, they have the input pins, the splitters, and the output pin already, and I just need to stuff it, so to speak, using the equation. All right. And Alexander is asking, can I see the layout of K1 real quick and the properties of the splitter? Sure. There we go. And here's the property of the splitter. I mean, this is like the default, okay? If I make a 3-bit splitter and I make it split, the fan out to be 3, this is the default. This is how it's going to be set up. All right. So now we get back to K2, and here is another kind of important question, because people ask, or some people ask, what do we do when we are making K2? So some people use the subcircuit of K1 inside the design of K2. That would defeat the whole purpose of having carry look ahead to begin with. Because K1 as a subcircuit has 2 levels of gates, so when the output of K1 is being used in the AND gate and then the output of the AND gate is ORed, now you have 4 levels of gate logic in terms of propagation time. And that is exactly what we're trying to minimize, okay? It's the propagation time. And the other thing that I thought would be obvious is if I am happy with this part here, that I can just go ahead and reuse the subcircuit of K1, I wouldn't need to go expand the expression so that it does not have any nesting. Okay, so the idea is to use the last form of the expressions, and I remember that I said that on Tuesday. Okay, so that means I don't know. I mean, I don't know how you're going to take notes, to kind of make sure that you're not missing the important parts of a lecture. But it is important to kind of take note when I say, okay, we want to use the last form or the most expanded form of the expression. I said that because there's a reason, okay? So now we look at K2, and then we just know that it has P1G0 in it. All right, so what we do is we use AND gates again. So we go to, we can use these AND gates over here. So we need how many AND gates? We need 2 AND gates. And then we need 1 OR gate. Okay, so we pick out all the components first, and they're all kind of too big. That's okay. We will change all of those to the narrow form at the same time. And I know one of them need to be a 3 input pin one, but we'll go ahead and change all of these to 2, and then just pick out the one that needs to have 3 inputs and change only that one to have 3 inputs. Like so. Oh, I picked the wrong one. Or I forgot to deselect first. Okay, deselect, pick one, change that one to 3 input pins. Alright, so now we are ready to go. So we go back to the equation. We see that we have P1G0. Okay, P1G0. So P1, okay, we can make it aligned like that. So here's P1, G0. Okay, so that makes one of the AND gates. And then the other one has P1, P0, and a K0. So the other one would take a tap from here. Now, whether you make it look nice or not, that's entirely up to you. This one looks really kind of ugly. I got wires flying over everywhere. Okay, but I just want to show you what it's supposed to look like. Okay, so we have P0, P1, and then we have K0 over here. So K0 is by itself going into here. And then we have the OR gate. The OR gate also needs 3 inputs. Okay, I forgot about that. So this one also needs 3 inputs. And then the output goes to the output pin, which probably should not be labeled K1 anymore, right? Because this is the K2 circuit. So this is now going to be labeled K2. And the one that is by itself is G1. So we pick out G1 and say you can go to one of the input pins of the OR gate, and then the output of the AND gate would go to each one of the AND gate would take its output to one of the input pins of the OR gate, and now we have the K2 circuit done. All right. And then Aaron asks, so in the 64-bit design, so these, if you fully expand a K64, then you will end up with a huge big mess, right? Because we'll have one AND gate that has 64 inputs, another AND gate with 63 inputs, another one with 62 inputs, and then the OR gate is going to have 60. I think it's 65. I think I counted incorrectly, so it's 65 inputs in the worst case. If you build it with carry ripple, it's going to look very clean and very neat because but it's also going to be very slow because of the propagation time of the carry going from one full adder to the next one. And then Marco has a question, so I'm going to address some of the questions first before I move on to K3. All right. So we got a question of, can we set up splitter input to? I do not know what that means. You mean hiding it, not make it show like this, that is kind of just dangling and not being used? Because I do not understand what the question is asking. Alright, so we got a few more coming in through the text channel. Could the new GAAFET creation process decrease the time for ripple carry? If it can, it is only going to be at a constant level. It is still going to be linear in relation to which bit we are working with. So it's not going to be super helpful. And then the next question is, not needed for K2, only for K3. Okay, so I think the original question is fan out 2. Alright, so when you guys ask questions or when you make a statement, please be specific because, so soon. So Mr. Song's question is not really kind of clear what it was trying to say. Just let the fan out to 2 and disable that bit. Yes. So we have done all of this already. Okay, this is what I meant when I said it earlier. We have done splitters from what? The first lab. Okay, and so this is nothing new. You guys got to kind of take notes when you do things. In the lab, you kind of either take notes or you remember how you do something or you go back and look up how you did something. Okay, because this class is about building things bigger and bigger based on what we have learned already. So that means this is going to be a trend. This is not a one-time thing. This is going to be a trend. There will be more and more stuff that we are going to build. So you got to make sure that you understand how to do things from the past, how you and also all the other concepts from earlier too. Yes, the labs can be reviewed as long as you have done it at least once. But if you haven't done it, then you can ask me to reopen it, but then I have to make sure that I do not count the score because, I'm not supposed to turn in something late. But yes, but once you have done it, you can review it. Okay. Yes, you can also watch my videos from past semesters, and there are many, many past semesters of videos to watch. Yes, that is correct as well. Alright, so now we can work with K3. So I'm going to work this all out, but I will not save the file and then distribute the file in Discord. So don't even ask me for that. And there's a reason for that, not that I want to be mean, but I want you guys to have to go through that process, okay? Because otherwise I'll be doing the work for you. And the thing is, people do not learn as well when they're not going to go through the process to do it by themselves. Alright, so we have K3 here. So K3 is a little bit more complex. We have 4 input stuff now. Okay, so we'll go ahead and go back to Logisim, go to the K3 circuit over here, and then the first thing is to collect all of those gates. So if you are kind of lazy, and you can always just kind of go like, I need one of these, I need one of these, I need one of these, and we'll make some changes later on. Control C, copy, okay, and then go to K3, and then just kind of paste it, somewhere. And obviously this one didn't I shouldn't have pasted over there, so we'll go ahead and paste it somewhere else where it does not make a connection to a wire automatically. I can't change the number of inputs, because these do not all have the same number of inputs. So I can only select the 2 that have the same number of inputs and say, nope, we need to up it by 1 at this point, okay? And then we can now take this one and up it by 1, 2. And then we make a copy of that, or duplicate. Control D is duplicate. And then this one will change it back to a 2. So we have 1 2 input AND gate, 1 3 input AND gate, 1 4 input AND gate, and then a 4 input OR gate as the actual gates inside this logic. And then the rest is just tedious work. Okay, the rest is really just wiring things up so that it is representing the equation or the formula that we have talked about in this module. Okay, so it's just a matter of looking at this expanded expression and then implement the expression using logic gates. So G2 is by itself. Okay, so we'll go back to Logisim. Okay, first thing first, change the output so that it is now K3 instead of K1. And then we said G2 is on its own going to the OR gate, so we'll make that one connection first. There we go. I'm looking at whether I'm connecting to an actual port, and that is the case. Okay, there we go. And now we look at the expression again. The 2 input one is going to take P2G1. Okay, so P2G1 is going to be with this gate. Now, if you are like me, who cannot really remember anything, you can always label the gate so that it tells you what it needs to do. So P2G1 can be the name of the gate itself, so this way you don't remember what is supposed to be connected to that thing. Okay, so we have P2, and then we have to take G1 to connect to it. Okay, oops. There we go. There we go. Alright, so working on the 3 input one, that one has P2, P1, and then G0. P2, P1, G0. So that would be this guy over here. And we'll move certain things out of the way. Okay, what was it again? P2, P1, G0. Okay, so we got these two. Okay. Okay, not this one. It's P2. Okay, I forgot. It's P2, P1, and G0, if I remember correctly. There we go. And then the 4 input one is going to handle the largest of the conjunction. I'm just kind of reading the text channel so I don't miss anything that is important. Okay. So we got P2, P1, P0, and then K0. Okay. So all of the individual P. Okay. So we can. That's P2. Okay. So we got P2. We got P1. We need P0. Okay. All the way from here. And I have to be careful because, I don't want this to interfere. Alright, so we can take it here, like that. And then we have K0 finally going into the last input of the 4 input AND gate. And now we just have to hook up the output of the AND gate into the input of the OR gate. Okay, so. Alright, yes, this is looking very ugly. There we go. And there we go. Whew. All right. And here we're done with K3. So we got K2, K1, K2, and K3. I didn't change the appearance. Okay, so the only thing that is super important for me to label is what kind of a circuit it is. Now, it doesn't really need to be labeled because if you pick up a K2 and you slap it into the main design and you pick up a K3 and you slap it into the main design, even though each one doesn't seem to have any name on top of it, if you click on it, it is clear. Because when you click on it, it will show you that this is a K2, and when you click on this one over here, it shows you it is a K3. And yeah, so from that perspective, and also combined with when you hover over a pin, it will show you the actual name of the pin. When you do not use a gigantic mouse pointer like I do, so combining with all of these things, it's going to be okay. But it is always nice. I personally prefer to label all the pins so that everything is visible and easy to look at. Because hovering over is okay, it works, but at the same time, you cannot just kind of look at the design when it's printed and know what is connected to what. Okay, so that's why it's still a good idea to label the pins and also the components, even though the tool can let you hover over a pin and show what pin it is. Yes, you can also copy and paste the labels too, which is kind of nice. All right. So now we go back to the quiz and see if I've done everything that needs to be done by the end of Tuesday's lab. All right. So once you have the K values, which we do now, okay, so you have to kind of do the wiring also. Note that all 3 circuits have P, G, and K0 as input. Okay. And once you have the K values, what else do you need to compute the sum as bits? Okay, so to answer that question, you have to go back to the notes because you have to know how the sum bits are defined. And I'm not going to give you the answer because if I just give you the answer, you're not going to remember that. But if you look up the notes, you will know at least where to look, and hopefully you will either highlight that portion or copy the definition into your own notes. Okay, just because everything is online doesn't mean that you cannot maintain your own notes. And I think it is a good idea to collect all the definitions into one place, so it's very easy for you to look up, oh, okay, I need to remember what the definition is for blah. Okay, you just look up a very short list and go like, oh, I can see how Q is defined for binary addition. It is like this. Okay, can I go back to the K3 circuit? So when I see questions like that, in my mind, I'm very, very tempted to say, but everything is being recorded. It is being streamed in YouTube, which means you can always, kind of time travel and go back to an earlier part and just kind of look at it that way. So what am I going to do? I'll show you. But, the point is, you should not need to look at this. Okay, this is supposed to be done on Tuesday based on the lecture and also the module that we have already talked about. Okay, so that's kind of the way I see it. Is I'm just repeating things that should be done on Tuesday already. All right, so moving on. So you guys can probably imagine what today's lab is going to be about, right? Finish the whole thing. Okay. There are a few more things that you need to do to finish the entire design. Because at this point we have all the kind of components kind of loosely placed, in this main design, and we know the output of the main design is going to have two output pins. Today's lab is going to talk about that, so I'll leave it up to you guys to kind of do this part. So we know the sum is going to be a 3-bit output, and then we also have an extra carry, which is K3. Okay, so K3 is its own output pin. So now, the question is, how do we wire up these extra components? That for the most part is what you're going to do in today's lab. So hopefully today's lab is not going to be nearly as bad as, well, I shouldn't say bad, nearly as involved and educational as the one on Tuesday. It's a good thing that I kind of turned off my camera because you cannot see my facial expression at this point. Involved, yes, involved. All right, so we are pretty much done with binary addition. So we're going to move on to binary subtraction. All right, so binary subtraction. But before we move on to binary subtraction, you probably notice a pattern of how I arrange topics at this point. Before I introduce something that you do not understand or probably have never been exposed to, I would introduce you to something that you already understand and then kind of work ourselves in the direction so that you get that part, right? So we are now in binary subtraction. This is the module that we are currently on, and I am certainly hopeful that most of you have at least read this module before class, because that's my recommendation. You always read ahead of me so that you are mentally prepared for the concepts that I'm going to talk about. Yep. All right. So now we're going to go back to the tablet because I want to give you some examples in base 10, and then we'll move on to base 2 examples. Okay. So we'll go ahead and, oh, okay, I know. Turn on the tablet. Okay, so here's the tablet. And we'll go ahead and perform a few base 10 subtraction first. So I will intentionally pick something that is easy to do, but at the same time, the result is going to be, what? Some people would say that. So we have 200. This is base 10, so we actually have 200. And we'll subtract, let's say 511. Okay, so we subtract 511 from 200. And most of you can look at this and go like, oh, that's super easy. It's supposed to be negative. Actually, my arithmetic is really bad. It is supposed to be what? Negative 311. Okay, no, that cannot be the case. Okay, I'll just work it out. All right, so we look at this, okay, and the typical way of looking at this is 0 minus 1 is a 9 with a borrow. And then we have 0 minus 1, which is a 9 again. 9 minus this borrow from the previously is going to be an 8 over here. And then we have 2 minus 5, which is a 7 with a borrow. And then 5 minus 1 is a 4. No, I take it back. It's okay. 2 minus 5 is a 7. 7 minus 1 is a 6. And then we have an extra borrow here. Okay, so when we look at it this way, people would go like this and go like, but this doesn't make sense. Okay, it doesn't make sense at all. And I say, yeah, it makes sense. It does make sense. Okay, so how do we look at this and say it makes sense? Okay, There's no negative 3, okay? So I would just literally write on the side and say 200 minus 511 is 689 with a borrow. But now the question is, what are we borrowing? Okay, what is this one representing? What are we borrowing? With a borrow of 1,000. That is what the borrow is about. Okay, so now we have to revisit the concept of a borrow. Okay, what does it mean when we have a borrow in subtraction? It means we don't have enough, for that particular digit, and we have to borrow 1 from the next digit, the more significant digit. Okay, so instead of looking at a multi-digit subtraction, we can look at a single digit subtraction first. So let me ask, what is 2 minus 5? So when we answer this question, most people, at this level in college would answer this question and say 2 minus 5 is negative 3, which is correct. Okay, but when we think about multi-digit subtraction, it is actually 7 with a borrow of 1. So the way we look at this is to say, Tak has $2 in his pocket. There's a bully, standing outside of the classroom who's going to collect $5 from Tak. And Tak doesn't want to be beaten up, when he steps out of the classroom, right? So what does he do? He approached one of his friends and go like, hey, can I borrow some money from you? But there's a rule: when I borrow money from that person, when I borrow money from that person, I can only borrow the next denomination. In other words, if I'm responsible for unit, for the number of ones, when I borrow a 10. Okay, so I borrowed $10 from my friend. So now I have $12 in my pocket. I step outside of the classroom. The bully comes to me and say, "Where's my 5?" So out of the $7, out of the $12, because I got 2 myself and then I borrowed 10, so I got $12. So of the $12 that I have now in my possession, because I borrowed 10 from my friend, I would give the bully 5 of them, right? So I would have 7 remaining in my pocket. So now the question is, what is my net worth, right? Because just because I have $7 doesn't mean that my net worth is $7. My net worth is actually negative $3, because even though I have $7 in my pocket, I owe my friend $10. So my net worth is still negative $3, except I didn't get beaten up. All right. So are we doing okay with this analogy, other than the bully part that people are now commenting in the text channel? All right, very good, excellent. So now I'm going to make a pitch for base 2. In other words, why I think base 2 is the way to go. For those of you who have younger children, or you have, nephews, nieces, who are currently trying to learn, subtraction, it takes a long time to learn subtraction. And the reason why it takes a long time to learn subtraction is because subtraction, unlike addition, is not commutative, which means, A minus B is not the same as B minus A. So that means, in terms of memorization, the table, or the number of entries that a child needs to memorize, is much bigger when it comes to subtraction when it is compared to addition. And that is one of the challenges of elementary school is, how do you get kids to remember 2 minus 7 is a 5 with a borrow, right? Because you need that in order to carry out multi-digit subtraction. But when we move on to base 2, it is easy peasy, okay? Yep, so you guys are all correct, okay? Because the idea is not how much money I have, on my hand. The idea is, what is my net worth, okay? So by borrowing money, I owe somebody else money. So my net worth has to take how much I owe into consideration, Now, I have no intention to turn this class into an accounting class, so I'm not going to talk about, asset versus liability versus blah, blah, blah. But the idea is, if I still owe someone money, I need to take that into consideration. And that's why when we have 200 minus 511, we have 689 as the answer, but that extra borrow, which is here, is really important because that means I owe 1,000. Okay, even though on my hand I have 689, I owe 1,000, and as a result, the net worth is 689 minus 1,000, which turns out to be negative 311. All right. Okay, I'm chuckling because I'm reading the text channel a little bit. All right. So 2 minus 5 is 7 with a borrow. So it's not just equals to 7. It is equals to 7 with a borrow. Okay, so that part is super important. All right, so to get to our terminology, okay, to get back to our terminology, we can say the single digit result of subtracting 5 from 2 is 7. Okay, so we use R to represent exactly the same thing, which is the single digit result, this time from a subtraction instead of an addition. So I use the same, symbol, but this time it means, it's meant for subtraction. And then for borrow, okay, if we want to say borrow, if I borrow 5, if I subtract 5 from 2, the borrow is going to be a 1. I can do something that is less tricky, right? So I can say, what about 7 minus 6? 7 minus 6 is a 1. And then what about the borrow? If I subtract 6 from 7, the borrow would be 0. So do we have any questions about what R and B are representing in the context of subtraction? So I'll let you guys think about this a little bit. Is the borrow 1 or 10? It is 1. It's the quantity that we are borrowing from the next digit. So it is still a 1.
Is the equation of x minus y or a remainder of x comma y?
That is a very good question. I like that question. The question is, if we want to implement the R and the B function for subtraction for a particular base, what would they look like? Okay, so I can go ahead and define that too. So I'm just gonna write it here. So we'll say unsigned, and in R we have unsigned again. Basically x is a single digit. Unsigned y, which is also a single digit. And in here, we have to be careful because it is possible that x is less than y, right? So the way we can fix this problem, once and for all, is we have to kind of know what base we are talking about. So we'll go ahead and do a pound defined, which is also the same, sort of the same thing as a const. So we'll basically say, base is defined to be 10 in this case. Okay, so we're dealing with base 10 numbers. So the way what I return in this case is I would just go ahead and always just add base to x first before I subtract y from it, and then we mod it. Okay, and then we just mod the whole thing with whatever base we have. So that would always work because if x is not less than y, then yes, then this part here is going to be exceeding the base, but since I modded with the base, I still end up with the correct value in the end. Is that okay? Does everybody understand the R function as I defined in on the tablet? I mean, you can plug in the examples.
That makes sense.
Okay. All right. And Keaton is typing, so I will keep an eye on that. So now we want to look at borrow, right? So borrow is actually very easy as well. Okay, so we got unsigned x, unsigned y. And borrow is really just a comparison. Okay, if x is less than y, then we return a 1, otherwise we return a 0. That is how we define borrow, the b function. Now the question is, some people may be asking, do you really need to use a ternary operator here? Just because you like to use the ternary operator doesn't mean that you have to use it every single time when it's not needed. Okay? For those of you who have taken my other classes, you know how I'm really fond of the ternary operator, because it really is a cool feature. Okay, it really is a cool feature of C and other languages that can handle a ternary operator. But in this case, it is actually needed, because if I just say return x is less than y, there's no telling which non-zero unsigned value it is going to return. There's no guarantee, because the C standard simply says that anything that is not 0 is representing true when we want a Boolean result. So if I just say return x is less than y, it could return an actual unsigned value of 3. Well, it cannot be negative because it's unsigned, right? But we have a huge number of possible values. If I just say return x is less than y, there's no guarantee that that is 1. By using the ternary operator the way I did, in the definition of b, now I basically say if x is indeed less than y, we are returning a 1 for sure. There's no other value that we're going to use when x is less than y. So this is actually important. Okay, the use of the ternary operator here is not optional. Okay, it is necessary. All right, so are we okay so far with what R is representing, what B is representing, and also the implementation of those two functions? Because if there are any questions about R and B at this point, now would be a good time to ask. All right.
So B is representing the borrow?
Yes. Yep. So B is representing the borrow when we have a subtraction of x minus y. So we got Luke typing, and we'll see.
Did you cut out for anyone else?
You mean the audio?
Yeah. Oh, I guess it was just me. You cut out on my end when you were explaining
Oh, okay.
what the borrow was.
I see. Okay, quick question. Go ahead. All right, so 1, 2 plus 10 minus 5 mod 10 return a 2. No. Why would it return a 2? All right, there we go. And we still got 2 more people typing, 3 more people typing, so I'm going to wait a little bit here. All right. So Chris is correct. Oh, nothing is going to be intuitive. If we stay with intuitive, there wouldn't be binary computers, right? And then we have, if 200 minus 511 has a borrow of 1000, then 2 minus 5 is going to have a borrow of 10. Yes, so the idea is the B function is only going to return the number of how much we are borrowing from the more significant digit. That's all it's going to say. Because when we're dealing with single digit subtraction, we don't know the actual position of that digit in a multi-digit, right? In a multi-digit situation. So all we can say is how much are we borrowing from the more significant digit, which is the digit to the left hand side of the digit that we are currently subtracting. All right. So 2 minus 5 could be in any position. Yes, that is correct. All right. I mean, if you look at the b function, it really is more or less a mirror image of the c function when we talked about addition. So it really is the same question. Why are we not saying that we have a carry of 10 and instead we say there's a carry of 1? I mean, it really boils down to the same thing. All right. So I'm gonna wait for the last question, hopefully. But if there are more coming, I will answer all of those questions before we move forward to talk about base 2. Because base 2 is super easy to talk about once we understand what base 10 is doing. Alright, so the question is, so the borrow in binary subtraction is similar to the carry in binary subtraction. I would say the borrow in binary subtraction is similar to the borrow in base 10 subtraction. Okay, and then we got one more person typing. And I'm just gonna wait a little bit. Alright, so there are no more questions. Alright, so now go ahead. Yeah, go ahead.
For the RBs on the left side, is that just basically going through that little algorithm you made on the right side then?
Let me read my own notes because I sometimes deviate from my notes. Yes, so in the notes in the module, I never really bothered to actually define B and R for base 10. I only defined it for base 2. But I did not bother to define it for base 10.
Okay, so like what you wrote in that tablet is just what you define on base 10.
At this point, yes.
Gotcha.
All right. Any other questions? Not really. Not really. So Chris, typed up an expression in the text channel, and that is not the case. Okay, because we don't put a subscript under next to b. B is always dealing with single digits. Okay, so it doesn't really matter which column in a multi-digit subtraction we're dealing with. It's only looking at one column at a time. Okay, so there's no subscript for the b. All right, so okay, so are we ready to move on to talk about how we adapt the functions that I have defined on the tablet to handle base 2? Are we ready for that?
Yep.
Okay. It's so simple, so easy that you guys look at this and go like, "Oh, really?" Done. Now we're dealing with base 2. It's the same logic, okay? It is exactly the same logic, okay? But the ramification of changing from 10 to 2 is huge, okay? Yeah, I might be spitting, because my mic is on the path of my mouth, so sometimes when I pronounce certain consonants, you might hear that pop. All right. So now we look at the ramification. Okay, the ramification is very interesting. Okay, because if you look at the b function, okay, so we have x, we have y, we have b of xy, and then we have r of xy. Okay, the base 10 version of this table is really, really long, right? But the base 2 version of this table only has 4 entries because when you're dealing with base 2, x can be a 1 or a 0, and y can only be a 1 or a 0. Because that's the whole idea. If you're dealing with base 2, you only have 2 digits, including 0. So x can be a 0, can be a 1. When x is a 0, y can be a 0 or a 1. When x is a 1, y can also be a 0 or a 1. Okay, so now we try to work out the b function. Now you can plug in all of these things into the function that we had on the previous slides. In other words, if you want to, you can go ahead and actually implement this logic here, all of this stuff here in C, and actually plug in the values and see for yourself. But I'll just tell you, okay, 0 minus 0 does not have a borrow of 1. 0 minus 1 has a borrow of 1. 1 minus 0 does not have any borrow. 1 minus 1 does not need any borrow. And then we look at the R function. 0 minus 0 has a single digit result of 0. Okay, I think we can all agree on that one. And I'm going to skip the second row and move on to the third row because those are the easy ones. 1 minus 0 has a single digit result of a 1. 1 minus 1 has a single digit result of a 0. So the one in the middle is the one that is kind of like, what about this one? Okay, 0 minus 1. Oh, I just move on to the next page. So when we have 0 minus 1, and we ask what is the single digit result of that, it is a 1. Okay, it is the same question as asking, in base 10, what is 0 minus 1? You would say it's 9. But that's because, 9 is the base minus 1. Because remember, when we are borrowing whatever the base is from the next digit. So in base 2, 0 is less than 1, so we have to borrow. But when we borrow, we are borrowing a quantity of 2. And then 2 minus 1 is a 1. So that explains why we have a 1 over here. So now we look at this table, which is based on our understanding of arithmetics. Okay, so this is not it's not based on base 2 or Boolean algebra or anything like that. This is based on our understanding of arithmetics. And just like before, we want to convert everything to make use of Boolean functions. Okay, and I'm lazy. I look at this table and go like, I kind of recognize the R function is something that we have seen before. When you look at this column here, I think we have seen it before. It looks to be the same as the R function in addition. Yes, indeed, it is the same. Okay, in other words, R of xy is just like before. It is x exclusive or with y. We are done, okay, with the R function. Okay, R function is the easy one. What about the B function? Well, as a very lazy professor, I look at the answer that my students are providing and go like, wow, looks like we can also use a Boolean function for B. So B of xy is not x and y. You go like, Tech, are you really sure that you can borrow those things from students? And when I go back to my own notes, okay, I can turn off the tablet for the time being. So when I go over my own notes, okay, I can see right here and say, hey, Tech, at one point in time, you actually knew that the b of xy is not x and y. Indeed, it is. Okay, but the bottom line is we can implement borrow as a function using only logic gates because we need only one NOT gate to negate the x, and then we need a conjunction and AND gate to take the negation of x, take y, and then the result is the borrow. And that's it. Okay? So you look at this, okay? Let me turn on the tablet again. So you look at this and go like, wow. So by subtraction and addition are not really that different after all. The only difference seems to be we need to negate the x first and then AND the y in order to get the borrow, and then the carry is really just the conjunction between x and y. So the only difference seems to be whether we negate x or not. Okay. There's no implication. Implication is negation of x or y. So even if we had an implication, it wouldn't be too helpful here. All right. So let's go ahead and do a few binary subtraction, just so that we understand the process to do it by hand. So we'll go ahead and work out a few scenarios. So we have 0, 1, 1, 0 minus 1, 0, 0, 1. Okay, that's 1. Okay, now we're dealing with base 2. Okay, so we work out, so once again we have x, we have y. I'm basically naming the rows in this particular logic. And then we have q again. You go like, but Tech, I thought q is only useful for addition. Nope, q is also useful for subtraction too. The next one I call it t. T. I name it t because t for take. I don't want to use b because b is already used as the name of a function. So when I want to name the components on the row, I want to use a different letter so that we don't have any confusion between are we talking about the function or are we talking about a destination of a row. So we have t, and then the last one is d for difference. Okay. So let me give you the definitions here. Okay, so q is defined exactly the same way as before. Q of I is x of I, exclusive OR with y of I. Okay, same as before. Yeah, t is to b as k was to c. Exactly. Okay, c is the function that will help us to compute those bits. Okay, and then k is representing the actual bits that the result of applying the c function. And in the same way with t and b, b is the function, and then t is the result after we apply the b function. Okay. So for q, it's the same as before. D is not too bad. Okay, D is also the same as before. So D of I is Q of I, exclusive OR with T of I. Because both of these are still using just the R function, and because the R function has not changed from binary addition to binary subtraction, so they look exactly the same. Okay, so D of I is kind of the same as S of I, because it is just relying on the exclusive OR between the Q and the T row in the case of subtraction, but in the case of addition, the T row is called the K row. But nonetheless, they are kind of the same thing. Okay. So the big question is, what about the T row? Okay, so now we'll take a look at the T row and ask, what about the T row? So now we go ahead and carry out some of the operations here. I'm just looking at this whole thing here, and I'm going to change one of the digits. I'm sorry that I have to make this change on the fly, but this will help us understand binary subtraction better. Okay, so what we'll do is we'll do the actual subtraction. So we have a 0 minus 1, and 0 minus 1 has a single digit of 1, but it also needs a borrow. So the borrow is going to go here because it's borrowing from the more significant digit, the one more significant digit to the left hand side of the column that we are actually subtracting. And then 1 minus 0 is a 1 here. And then here we have 1 minus 1, which is a 0. And then we have a 0 minus 1, which is a 1 with a borrow. And now we have 1 minus 0, which is a 1. 1 minus 1 is a 0. And then we have 0 minus 1 being 1 with a borrow. 1 minus no borrow in this case, which is a 0. So 1 minus 0 is a 1. Okay, so we are now done with the binary subtraction. But the most important point is, hey, there seems to be two ways that we can have a borrow of 1. Okay, because in this case, x minus y makes this borrow of 1. But in the second case, we have q minus t, which is resulting in a borrow of 1 too. Just like there are two ways to have a carry of 1, there are two ways to have a borrow of 1. Okay. So now the question is, how do I write out the T of I equation? So the T of I equation seems to hinge on, or T of I plus 1 I should say. So T of I plus 1 seems to hinge on the borrow, or whether there's a borrow of 1 or not, when we subtract yi from xi. And it also seems to rely on the subtraction of qi minus T of I. So now the question is, how do what operator do I use to combine these two. Okay, so you have to think about this situation kind of the same way that we thought about the carry situation. So I'm reading the text here. Are we implying that the two types of borrowing are propagate and generate, just like the carry operation? That's exactly what we are talking about. Yes. So Andrew is 100% correct in this case. But let's go ahead and kind of evaluate this situation here. Okay, t of I plus 1 can be coming, a borrow of 1 can be coming from x minus y. The borrow of 1 can also be coming from q minus t. So can we use an add here? Okay, so here's a question. Or can I use a or here? Okay, so this is the same question that we asked on Tuesday when we talked about the carry situation. So it's the same way. Okay, we have to look at these two and see if they can both be ones. So we look at the b of xi yi. We look at the b of qi ki, and we ask, can both of these be ones? So now what we do is we make a truth table, xi yi. I think that should be sufficient. There we go. Oh, we also need to take a look at ki, because ki is not determined by this particular column. So ki is independent to xi and yi. So we got 8 entries in this case. So this is a slightly different way to analyze this scenario. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. Okay. So now we can, you guys can go ahead and plug in the equation and figure out, the b between xi, yi, and so on. So we'll go ahead and take a quick look over here. 0. So the only case when we have a borrow, when we subtract yi from xi, is when xi is a 0 and yi is a 1. So that would be these two rows over here. And then for all of the other rows, the result is going to be a 0. So we got 0, 0, 1, 1, and then all zeros down here. 1, 0, 0, 0, 0. There we go. And then Chris is mentioning that P and G seems to be common elements to help simplify the circuits. That is correct. It is to simplify the analysis of the relationship between t of I plus 1 and t of I. That is what the P and G's are for. P, by the way, is the abbreviation of propagate, and then G is the abbreviation of generate. So we end up with the same configuration of propagation versus generation. So we'll get to that part in just a little bit. Ki or Ti. Did I mistakenly use? Oh, yes, I did. Okay, thank you. So this is T of I, not K of I. And same situation over here. There we go. Thank you. All right, so now we look at Q of I versus T of I. But we have to first think about what is Q of I, because Q of I is dependent on X of I and Y of I. It is the exclusive OR between those two. So in here we have a 0. In here we have a 1. These two are guaranteed to be zeros. These two are guaranteed to be zeros. This one is a 0, and this one is a 1 over here. You look at this table and go like, okay, so what is the big deal of this table? Well, the big deal of the table is to try to answer the question of, do we need to use an arithmetic addition, or can we substitute the addition with an OR? The difference between an addition versus a logical OR is whether the two b functions can be ones at the same time. That really is the question. So when we analyze this, table over here, we can see that there is not a single row that we end up with two ones. In other words, there's not a single row where the borrow of xi yi is a 1 and then the borrow of qi ti is also a 1 because we got, okay, none of them is a 1, 1 is a 1, 1 is a 1, 1 is a 1, none is a 1, none is a 1, none is a 1, and 1 is a 1. Okay, we don't have a single row where the two borrow functions return a 1 at the same time. So that means it is perfectly okay to use a logical OR instead of an arithmetic addition. If this is ringing a bell, okay, that you say, but Tech, didn't you talk about something like that in a previous class when we were talking about addition? Well, congratulations, you were paying attention. Very good. Yes, I did. It's the same analysis. Okay, it really is the same analysis. So now that we found so much similarity between addition and subtraction when we are dealing with base 2, the next question is, can we use that look ahead mechanism that we talked about on Tuesday when we are subtracting now? Okay, because without that mechanism, I can see that t of I plus 1 relies on t of I. Okay, so can we somehow use some trick so that we don't have to have that linear dependency? And the answer is yes. Okay, so that's why we have section 6 again. And this time with section 6, I'm just going through a whole bunch of Boolean algebra stuff. Okay, I'm not going to go through each line to explain how they work because we are out of time. I didn't realize that we were out of time by 3 minutes. So I'll just kind of quickly finish up this section because to stop now and to restart this on next Tuesday is an ineffective use of time. I'll give you that time back in the lab and stuff like that. We're 13 minutes over. Yes, and you don't have to pay a single penny for the extra time too. Yeah. Yeah, not that you guys really want me to go over time, right? But the bottom line is t of I plus 1 can be expressed in this form. Okay? But by redefining, and you can see how RE is underlined because it is not exactly the same definition as for addition. But if we decide to redefine G to be the negation of xi and yi, and we redefine p of I to be the negation of xi or yi, we end up with something that looks almost exactly the same as what we have seen with addition.
Professor, could you
Yes.
please read the screen?
Oh, right. I forgot about that. There we go. So, after that whole bunch of Boolean algebra manipulation, we end up with this. Okay, we end up with t of I plus 1 is g of I or p of I and t of I. You look at this and you say, other than we are calling things t instead of k, isn't this identical to the one that we saw on Tuesday when we talked about carry look ahead mechanism? Well, once again, congratulations, you have been paying attention. Good for you. And the answer is yes, we did. Okay, if you change this t to a k, and you change this t to a k, and you change how g of I and p of I are defined, you get back to addition. So that means the general how should I put it? The mechanism to generate t of n plus 1 in this case is identical to the mechanism to generate k of n plus 1. The only difference, is whether we negate x of I first, when we define g of I and p of I. That is the only difference between addition and subtraction. It boils down to just whether we negate x first or not. Whew. Okay. So we are done with binary subtraction because we just borrowed most of the arguments from binary addition. So now it is time to release the new lab tonight. The new lab tonight is it's just staying on carry look ahead, so it has none of the subtraction stuff. So you guys should have should know enough to start with that lab already. I mean, indeed, at the end of Tuesday, you already have enough to start on the lab tonight. But I didn't assign it because it would take too long to complete. So now we're going to go to carry look ahead adder part 2. And most of you will think, oh, I know what the key is going to be. It's going to be 3x3 part 2. No, that is not the case. I changed it. The key is 3x3b. 3x3b is the access code to the lab. And this time I will be careful to say when it's due. Because some of you are very careful when you listen to me, which is good. So it's going to be 9:50 p.m. Pacific Standard Time. Because someone's going to say, so 9:50 p.m., but you didn't specify the time zone. So once again, all the labs are due at 9:50 p.m. of the day that I assign the lab, unless I explicitly say otherwise. Okay. Save and publish. Well, if I had used UTC, I think that time has passed already, because UTC is ahead of us. Alright, so save and publish. Now it is released. Alright, so for those of you who did not get the lab done or the way that you would want to have it done by the end of Tuesday, you can rewatch the beginning of today's lecture to recreate that portion of the lab and then continue on to part 2 for this particular lab. Alright, so I'm gonna go take a short break and I'll be back in about 10 minutes. Where do we submit your file? I need to reopen another assignment for that. Yeah, this is one of the things. Let's see here. Yep. So I have another assignment, just for collecting the file. And this one does not have a key, so once I open it, it's open. Okay. So I'll have the same due date for this one, FEB4 9:50 p.m. FEB4 9:50 p.m. Click save and publish. There we go. So we have an assignment, a separate assignment to collect the file that you would have created by the end of tonight's lab. There you go. So that should answer the question of where to submit the file. Very good. Good question. I almost forgot about that. All right. Excellent. So I'm going to leave you guys to get started with the lab. I'll be back in about 10 minutes to answer questions. And also, if you are asking questions, using the direct message is a better way to do it. So just go ahead and utilize the direct message. I will still answer the questions in the text channel for the whole class. Yeah, so it's up to you. Use either way. Alright, so I'm gonna stop the live stream and then I will take a little short break and then I'll be back to answer questions.